Yesterday we looked at tangents and normals, but using the parametric coordinates. Today we're going to look at tangents and normals, but using the Cartesian coordinates, so an alternative approach. Let's see what happens. So our tangent, so again we've just got our basic parabola x squared equals 4ay. But this time, instead of the point being 2ap ap squared and its parametrics, I'm just going to say, well, x1, y1. It's got some Cartesian coordinates. And again, we're going to find the equation of the tangent. It's all right. However we find the derivative, and we saw yesterday there were several ways we could do it. I'm going to make y the subject, differentiate x on 2a, but now I'm substituting in the Cartesian coordinate x1. So dy dx becomes x1 on 2a, which means the slope of the tangent is x1 on 2a. Put that in a point slope formula. Now I'm going to rearrange this, but I'm going to write it in a very strange way. 2ay minus 2ay1 is x1 minus x1 squared. But I know x1, y1 is on the parabola. So therefore, x1 squared must equal 4ay1. So you'll see I've changed my x1 squared over there to 4ay1. Now on the other side, I had a 2ay1. I said I'm going to write the equation in a very strange way. x1 is equal to 2ay plus y1. But there's a reason for writing it that way. It looks like the equation of the parabola itself. Now you might not see it straight away. But have a look at the equation of the parabola. It's x squared equals 4ay. On the left hand side, yes, I don't have x squared. I've got x times x1. Well, imagine that 1 wasn't there. I'd have x times x, which is x squared. Now have a look at the right hand side. Now I don't have 4ay. What I've got is 2ay plus y1. But again, if that 1 wasn't there, I'd have 2ay plus y, which is 2y, 4ay. So the actual equation of the tangent mimics the parabola itself. So that's why I've written it in that format. Okay. Well, what about the normal? What happens there? So again, our standard parabola, Cartesian coordinates for P, but now the line's at right angles to the tangent. So our slope would now be, well, slope of the tangent was x1 on 2a, so the slope of the normal will be minus 2a on x1. Sub that into the point slope formula. Let's play around with that one. x1y minus x1y1 minus 2ax plus 2ax1. Well, the only pattern I can really do there is to make the left hand side sort of look like the right hand side. So you'll notice that on the left hand side I've got 2ax plus x1y, but then the constant I've put on the right hand side, 2ax1 plus x1y1. Because remember, x1, y1 are actually numbers that we'd be substituting in. So the right hand side is all a constant. But in this case with the normal, the right hand side is mimicking the left hand side. So where we had on the left hand side the variables x and y, on the right hand side it's replaced with x1, y1. So I don't think it's quite as nice as the tangent mimicking the parabola itself, but there is some sort of copying happening there. Now why use Cartesian instead of using parametric? This sort of question, whether they have questions about lines cutting or touching or missing the parabola altogether. So alright, here's our parabola. So a line could cut it, hit it in two places, could touch it, is a tangent, or misses it altogether. Now I know the general form of any of those straight lines, well not the general form, but the standard form is y equals mx plus b. So each one of those could have the equation y equals mx plus b. And I know they would meet, well, if I wanted to find those points, I'd solve them simultaneously. So instead of saying x squared equals 4ay, I'm going to say x squared equals 4a mx plus b. Because y equals mx plus b on the line. And I'm going to rearrange that and form a quadratic equation. Because with quadratics, I've got something that tells me whether this equation has no solutions, one solution, or two solutions. What is that thing that I'm thinking of? Discriminant. Okay. So I don't actually have to go and solve the equation to find out whether the line cuts it, or touches it, or misses it. I can just use the discriminant. So I know there'll be two solutions, or I'll cut it when the discriminant is greater than 0. There'll be one solution, or just touches it, so it is a tangent. Now that idea is quite common. When we have to prove something is a tangent, we just look and go, okay, well, I'll find when the discriminant is equal to 0. And misses it altogether when that discriminant is less than 0. Now if I actually work that discriminant out for the general situation, we've got minus 4am all squared minus 4 times 1 times minus 4ab. And we end up with 16a outside of am squared plus b. Let's have a look at the situation. Two solutions. Hang on, I haven't written the whole thing down. And the reason is 16a, remember our standard parabola, a is going to be positive. So 16a, it doesn't matter. It's the am squared plus b that's going to make it positive or negative or equal to 0. So it's just that bit that I need to worry about. So I know it'll have two solutions. When am squared plus b is greater than 0, when it's equal to 0, it'll be a tangent. And when it's less than 0, that's when it'll miss it altogether. So I guess that's the advantage of using a Cartesian equation as opposed to a parametric equation. Same question as yesterday though, but I'm going to take it using that Cartesian idea. So we're going to find the equation of the two tangents that pass through this external point. So 3, 2 is not on the parabola, you remember, it was an external point. And from that external point, we could draw two tangents. So I'm going to say, well, I know the tangent will be of the form y equals mx plus b. All lines are in the form y equals mx plus b. But I know the tangent goes through the point 3, 2. So if I substitute that in, I get 2 is 3m plus b. Make b the subject. So I now know the tangents, instead of saying y equals mx plus b, is y equals mx plus 2 minus 3m. All I now need to know is m. What are the slope of the lines? Well, x squared equals 4y is the parabola. So we're going to solve them simultaneously. Let's make it, instead of 4y, I'll make it 4 times mx plus b, but b is 2 minus 3m. Create the quadratic, and there's that common idea I'm going to use. If it's a tangent, then the discriminant will equal 0. There will only be one solution to this quadratic. So solving that, there's my discriminants. 16m squared, 16 goes into everything there. M squared minus 3m plus 2 equals 0. You'll notice it's the same factorisation that we got yesterday. So either m equals 1 or m equals 2. Sub that back into my equation up here, y equals mx plus 2 minus 3m, and I've got my two tangents. So the same two lines we came up with yesterday. So same problem. Yesterday we solved it using parametric coordinates. Today we did it via Cartesian coordinates. Alternative approaches. So if they just give you this question, up to you how you do it, which way you prefer.